All right, so I'm going to be interested in representations of a group like this, a presentation, finite presentation, into a semisimple group. So this is a semisimple algebraic group. And I'm going to look at it over the complex numbers, so over C. So for example, you could think just of SL2C, that's already a very interesting case. So I'm going to be looking at XW. So W bar is the tuple of relators, and XW is the representation variety gamma W psi G. So it's a set of all homomorphisms from gamma W to G. And I will look at curly chi or curly X of W, what's called the character variety. So that's XW bar quotiented by G through the GIT quotient. So this is called the character variety. And it's basically the moduli space of representations. So double bar is called the GIT quotient. So it's basically the quotient where you act by conjugation. But double bar means that you make this into an algebraic variety. So this is an algebraic variety, and it is the algebraic variety whose coordinate ring is the coordinate ring of the representation variety, and you take the invariance. Okay, so that's how it's defined. And the action is by conjugation. Okay, you post-compose by conjugation. So this is called the character variety, and I'm mostly going to be interested in a subset of the character variety, which I put a superscript Z here on top. This would be called the Zariski-dense part of curly X W. And what this is, it's a certain Zariski open set in the character variety, which is defined as as XW intersected with a Zariski open set omega quotiented by G, and omega here is the non-degenerate locus. So it's the complement of what I called the degenerate locus in the first talk this morning. So it's a set of tuples in G to the K, which generate a Zariski-dense subgroup. Okay, so this little G here is the complex point of an algebraic group. Okay, so it turns out that this is actually, it's clear that it contains an open set, Zariski open set, but it actually is open. So this can be shown. In fact, it can be shown that there are two finite dimensional representations of G with the property that a subgroup of G is Zariski-dense if and only if it acts irreducibly on both representations. So an acting irreducibly is obviously a Zariski open condition. So this is a Zariski open set. What's outside this Zariski open set is a closed, therefore a closed Zariski closed subset, contained in the character variety, which is a Zariski closed subset made of tuples that generate a proper Zariski closed subset, or a proper subset. So somehow they live in they don't live in G, they live in a smaller subgroup. Okay. So I'm going to be interested in the following questions. So first of all, can we say something about the dimension of this character variety? So it also makes sense to ask what's the dimension of the full character variety, not the Zariski-dense part. But typically it may not be the same. So the degenerate part can contribute to a larger component with a larger dimension sometimes. So I'm mostly going to be interested in this. Can we understand the number of irreducible components of this? Now, another thing is that, as you see, right, so maybe I should have said first, but this XW here is an algebraic variety. It's a set of G1, Gk in G to the K, which satisfy the R relators. Right? So this set here, the representation of variety is given by these equations. Okay? It's given by these W equal 1. So in particular, if G is defined over Q, the Galois group acts on this variety because these words are just words, so they have no constants, so the Galois group can act. Yeah.
Say here XW is the Zariski-dense part. It's the definition, right? It doesn't imply that it is Zariski-dense as a subset of XW, right?
It will be, because this omega is Zariski open. Yeah.
But then how can the other guy can have larger dimensions?
Yes, that's right. I mean, it will be. So it depends. It depends on the if it's irreducible or not. So if XW is irreducible, then it's a Zariski open set and a Zariski dense. But sometimes it's not irreducible, and then you may have a degenerate part, which is a component of higher dimension, and I'm disregarding this.
And then it won't be a Zariski-dense subset of the entire thing.
Of the entire thing, no.
Yeah,
But only, yeah, right? Okay. Yeah, that's right. So, okay. So yeah. So you have the Galois action. So the Galois group acts, and so you can ask, what is this Galois action? So it acts where? It acts on the components, on the geometric components. Of this character variety. Another question is, okay, so how about, so it's a, the question is, what's the Galois action? So is the Galois action transitive, for example? If it's transitive, can you say if it acts by the full permutation group? No. Now, how about singularities of this character variety? Is it a smooth variety usually, or not? And another interesting question is, I mean, so a point on this variety gives you a representation. So you would like to know if this representation is faithful, or is it discrete sometimes in C. So what is the locus of discrete representations, of faithful representations? Okay. So I'll give you some examples. So, for instance, it could very well be that gamma bar is, as an abstract group, is a higher rank lattice. In which case, you know by Margulis that the character variety is finite. And sometimes just 1 point, if it's higher rank. So, if that's the case, when you are finite, I will say that the group is G rigid. What this means is that if you have this representation given by a point in this character variety, then you cannot deform it, so because it's finite. So say that it's G rigid. Another piece of terminology, I would say that gamma bar is Galois rigid. If not only it's finite, but the Galois action is transitive. So to say that Galois action is transitive is the same thing as to say that it's Q irreducible. It's reducible over Q. So it's harder to find lattices that are Galois, I mean, to prove Galois rigidity. But for an example of Galois rigidity, here is an example. You take PSL2 Z bracket omega. This is the cubic root of unity. This is Galois rigid. This is PSL2 Galois rigid, and this was first studied in the context of profinite rigidity. That's in the paper of Brightson, McReynolds, Reed, and Spittler. Okay, so another interesting example here is when the group is when the presentation is a surface group. This has been studied quite a bit. So. Yes, stronger. So I want finite character variety, but also transitive action of the gamma group. So suppose gamma omega, or gamma W is pi1 of a surface, bigger than 2. Then it's known in this case that the character variety, even the entire character variety in this case, is irreducible. And has the right dimension. For every G. Okay. If you give G semisimple, then it's irreducible. Okay. And the dimension is 2G minus 2 times dim G. So this is a theorem. It's a theorem of Rapinchuk. Benais and Chanusov. I think they proved it for SLN, I think, and then it was generalized by Liebeck and Shalev for arbitrary G. And the way they proved it, the way Liebeck and Shalev proved this, interestingly, is by counting. So the way they prove the dimension estimate is by looking at the FP points of this variety, which essentially measures the. So if you look at let's say the full homomorphism representation variety, this is essentially the homomorphisms from the surface group, to G of Fp. And if you can count how many homomorphisms there are to G of Fp, then you can therefore have an estimate on the size of this character variety. And they prove that it's, when P is large, this is roughly this. Okay? And therefore, by Langevale, this tells you the dimension over the complex numbers. But how do you prove this estimate? Well, you need to count these homomorphisms. So you need to count the solutions in G of Fp of these. You need to count how many. Okay, so this pi1 of surface. I remind you, this is the group generated by A1 AG, B1 PG, with a single relator, which is of the form product of AI BI equals 1. Okay. So here in the surface group you have a single relator and you have 2G generators. So you need to count how many group elements in G of Fp satisfy this relation. And fortunately this can be done using character theory. In fact, there is a formula due to Frobenius that allows you exactly to prove this. So to prove how many, to count using character theory, to count how many solutions there are to this equation in a group like G of Fp. Okay, so inspired by this, we're going to answer. We're going to at least answer the first question there, the dimension. Okay, so yeah, I'll give you a couple other examples, and then I'll state the theorem. Right, so this character variety can be empty. So chi can be empty. Sometimes you have groups, you have presentations with no Zariski-dense image in any semisimple Lie group. And so that's the case, for example, if you take the Bohm-Sachs-Solitar group. AB is A, B equals B to the M, and the GCD of NM is 1, and M bigger than 1. So this is the non-solvable Bohm-Sachs-Solitar group, and it's easy to see that any matrix image of this, any matrix representation of this, has to be virtually solvable. In fact, if you have a matrix, this is A. If you have a matrix A whose mth power is conjugate to the nth power, it implies that A has finite order, and you can work a bit more and show that there is no image into a semisimple Lie group which is Zariski-dense. Another example here, a very concrete example, is this one. You take a one-related group, A squared, B, A minus 2, B minus 2, in SL2. So that's just one relator and two generators. This group has been studied by Cornelia Drutu and Mark Sapir. And they show that this group, so gamma W, is residually finite. But not linear. And if you try to understand what's the character variety for this, you can write down the equations. And you'll realize that the character variety is just 2 points that are permuted by Galois, and therefore it's Galois rigid. So it's Galois rigid in SL2. And you can give coordinates for these points by looking at what's called the Frege-Klein coordinates. So this is trace of A, trace of B, trace of AB. So in SL2, these are called the Frege-Klein coordinates. So these are coordinates for the character variety of the free group in SL2. Okay, so they determine these coordinates. They determine the pair AB up to conjugation. And the 2 points in this case have they have these coordinates which square root of 2, -1, and -1 over square root of 2. This one and its Galois conjugate. So minus square root of 2, -1, 1 over square root of 2. So these are the 2 points that belong to the Zariski, so you can show the Zariski-dense. So there are two representations of this group with the Zariski-dense image in SL2C, and they are Galois conjugate this way. I was particularly interested in this particular example because here you see you have 1 over square root 2, and so in particular it's not integral. So it's not an integral representation. And on the other hand, it's a rigid representation, it's even Galois rigid. And there was a question by Hélène Hainaut a couple of years ago, and she was, because she has very interesting work where she shows that the pi1 of projective varieties have this property that rigid representations are integral. And so this shows that there are finally presented groups very far from being pi1 of projective varieties that are rigid but are not integral. Okay. No, it's not faithful because Drutu Sapir shows it's not linear. Okay. Yeah. Is the image free? I don't know. I don't know much about the image. I don't think it's free, no. What do you mean, the image?
Yeah, like the image of these.
So they satisfy this, right? So it's not free. But I don't know much about the image, so yeah. So that's a very good question, actually. When is it faithful? I can say one thing about this. But maybe I'll say it just not now, soon, not now. Yeah, so. Right, so a good test ground when you think about this problem is to look at SL2C. Because as I said, in SL2C you have these Frege-Klein coordinates. In the particular case when you have 2 generators and 1 relator. So when you have 2 generators and 1 relator, as I said, you put x equals trace of A, trace of B, and z equals trace of AB. And then if you look at the trace of a word in A and B, well, this is some polynomial in x, y, and z. And this polynomial belongs to z bracket x, y, z. So that's a fact that for every word, there is a word polynomial with integer coefficients, such that the trace of a word in A and B is the polynomial evaluated at the trace of A, the trace of B, and the trace of AB. The proof of this is very simple. You write down your word, and you use the Hamilton-Cayley theorem, which you have this, because you are in SL2, you have this. So in particular, you have that A inverse equals x minus A. Okay, in the group algebra. So whenever you have an inverse, you replace the inverse by x minus A. When you have a square, you replace the square by 1 minus xa. And so you expand all of this. And so you write down your word as a linear combination of A, B, AB, and the identity with coefficients that are all polynomials in x, y, z. Okay. So that's why you have this. And then with these polynomials, you can define equations for the character variety. So it's defined by the following equations. PW, the trace has to be equal to 2 because you want W to be the identity, but you also want PAW to be X and PBW to be Y. So these are three hypersurfaces, and the intersection of the three hypersurfaces define my character variety. Okay. I want the Zariski-dense part, so I have to remove from this the degenerate locus, V-deg, which is the complement of this non-degenerate locus. But V-deg, in this case, you can completely give equations for it. So V-deg is a union of a subvariety, a hypersurface, delta equals 0, where delta is a polynomial x squared plus y squared plus z squared minus xyz minus 4. It's the polynomial that comes from the trace of the commutator. And you also have the coordinate lines, like x equals y equals 0. You have three coordinate lines. And you also have a finite set. This finite set corresponds to finite representations, so finite irreducible representations into finite subgroups of SU2. So finite irreps, you have a finite set. So here, these ones correspond to dihedral representations. So these are representations whose image has a finite index subgroup, index 2 subgroup, which is diagonal. And these are the representations that are not irreducible on C2. Okay, so here for SL2 you have a complete description of the degenerate locus. So in particular you can ask a computer algebra system to compute the equations for you, and then to ask what's the dimension, how many connected components there are, and so on and so forth. Okay. In particular, you can do this for this word. Okay, so now about theorems. Okay, so it starts with the theorem of Alex and Gadi. Fairly recent theorem, 1318. They showed that if you pick the relators at random among words of length L, and maybe I change the pen here. That's good. And L is going to tend to infinity. Okay. And also, the number of relators is going to tend to infinity. I think they need at least log L. In the paper they talk about positive density, which would imply something stronger, but they need only log L. And then they show that with high probability, as L tends to infinity, the character variety, the Zariski-dense part, is empty. Okay. For every G. In fact, they prove something slightly stronger. They show that with high probability, all G representations of gamma W have trivial image.
Here G is fixed.
G is fixed. Yeah, trivial image, or depending on parity, you could have sigma 2z. So G is fixed. Okay. So this goes. So G is fixed is very important because we know by work of Wise and Hegel that typically these groups, these finally presented group, they will have small simplification 1/6. In particular, they will be virtually special, and they will embed into some RAG. In particular, they embed into some GLN of Z. But for an n which is very big and depends on the number, on the presentation, so it will depend on that. Okay. So.
The parameters are high, it's not clear that it will have any representation in any.
Yeah, it depends on L. Right? It depends on everything.
The ratio between R and L is connected.
So.
Yeah, here you just assume like it grows larger than log L. He's saying that if it actually grows as an exponential in L or something like the Gromov density module, then from some density we don't know if that's correct. You have only a lower bound
Yes.
now. If
Oh,
you need
sure.
also an upper bound now.
If you know that you are C prime 1/6, then you have the theorem. Okay? Yeah, thank you. So, yeah. So if R of L is like, yeah, no, E to the,
1/12. Yeah.
right.
Yeah.
Depending on C, then you will know. Okay. Yeah. Okay, so this what we did was to start understanding this proof and try to understand what happens if the number of relators does not grow to infinity, but remains bounded. Okay? So I can state the theorem here. So maybe this is better. Yeah. Okay, so this is now the theorem. Okay, so again you're going to pick W1 WR at random, but R will be fixed among words of length L. So L will tend to infinity. And then the theorem says that with probability, with large probability, so with probability at least with actually exponentially few exceptions. So here the number of exceptions just goes to 0 when L tends to infinity, but here number of exceptions goes to infinity exponentially fast. Then we have the following. So C here is some constant depending only on G. So first of all, if R is at least K, then this Zariski-dense part is empty. Second, when R is K minus 1, then it's finite. K is the number of generators. Okay, and R the number of relators. So this is finite, and Q irreducible. So we have a Galois-rigid situation. And C, so maybe I'll move this a bit. And C, when R is smaller than K minus 2, then the Zariski-dense part is geometrically irreducible. So it's an irreducible variety. And it has the right dimension. So it's K minus R minus 1, G. Right, so I deleted the, yeah, never mind.
This recovers, for example, the surface group.
Yes, so it's a so it doesn't recover the surface group because it's a random statement, so it's a statement about random presentations. But it's of the same, the dimension formula is the same. The dimension formula is the obvious thing that it should be, because you have k degrees of freedom, you have r constraints, and you remove one because you take the action by conjugation, so you take the character right. Okay? It's the same as 2g minus 2, okay, in the surface group case. Okay, so the most interesting, so I should say, I have to say that this theorem unfortunately is conditional, and we can only prove it under GRH. Okay, even though it looks like it has nothing to do with number theory. So, yeah.
All parts. Which parts?
Yeah, all parts. So this part is the most interesting one. I'll come back to this. Some remarks. So what is GRH? So it means that the zeta function, the Dedekind zeta function of a number field has its zeros. It's not trivial zeros. On the real line, on the critical line. We don't need the full power of GRH, but we need something which people consider just as hard. Somehow we need that epsilon GRH, which means that there are no zeros in a disk of around 1 of a certain radius, and we need the radius to be at least 1 over the log of the discriminant of the number field to some small power epsilon. And it's not known, so the best known estimates say that when epsilon starts to be equal to 1, then it's known that there can be at least, at most 1 zero, a zero in this disk. But even a zero would be a problem for the proof. Anyway, and so the known estimates are much worse than this. But that's all we need. 2. Yeah. So what is the field here? So K is a number field. So it's important that it's an arbitrary number field. What will be the number field related to this? K will be the fields of definition of the connected of the irreducible components. Irreducible components of the character variety. Okay, so this character variety comes with irreducible components. They will be typically defined over some number field because the full character variety is defined over Q. So they will be defined over some number field depending on how many there are. And this number field typically will be quite large. We'll have a degree typically of degree L, so the length of the word. So the degree tends to infinity. So we need this GRH for all these number fields. What? Yes, the discriminant, we have a bound discriminant which is needed for the proof to work, and it's given by what you get when you have equations with height exponential in L, right? So the words are basically equations with integer coefficients and heights 2 to the L, and so that's what you get when you compute the discriminant. Okay, so time? 10 minutes? Yeah. Okay, so,
And then you have 5 for questions.
yeah, good. So I'll try to wrap up. So, yeah, one question about faithfulness. You can show that it's usually not faithful. Actually, so I can show this for SL2, but I don't know it for in general. So in SL2 there is a simple thing that allows you to show that it's not faithful. Usually it's the fact that if you have 2 generators and 1 relator, let's say, then there is something called the Magnus Freiheitssatz, which tells you that when that these things are not isomorphic as groups unless W and W prime are conjugates in the free group. But on the other hand, in SL2, you have a relation between the character variety associated to a word W and the character variety associated to its reciprocal. So if you look at W hat of AB to be W of A inverse, B inverse, inverse, so that's the same word but read from right to left instead of left to right. Then you can see that PW, the trace polynomial, is equal to PW hat in SL2. That's a, yeah, it's because trace of A, trace of AB, trace of BA. Yeah. So, and it only depends on the trace of A, trace of B, trace of AB. So this is true in SL2. And so therefore, the character varieties will be the same. And so if W is not conjugate to its reciprocal, then yeah, right, of the free group. Yeah. Then you get that that gamma W is not faithful in SL2. Okay, but this doesn't happen for a random word. For a random word, this doesn't happen. So for a random word, it's not going to be faithful. But that's pretty much the only argument I have to show non-faithfulness. Although I'm pretty sure it should probably never be faithful, at least with high probability.
What do you mean by this being faithful? That a generic element?
Yeah, I mean that's right. A generic element in here not be a faithful representation of gamma W.
It does happen. It's not conjugated.
It's not. Yeah, so it's not faithful. Yeah. Right.
You prove that it doesn't contain any faith One of them.
Yeah, in this case, yeah. That's right.
So you suspect non-faithfulness in SL2 or
I expect non-faithfulness in general for generic representation. Yeah. I mean, and therefore for all. But of course for a random word, because we know that there are nice linear groups that have finite representations. So in some sense, they should not be random. They should be very special groups. Okay, so I said this is somehow the most interesting bit here, this one, part B. Because with part B, you get that this is finite. So it gives you finitely many points. And each of these points generates a Zariski-dense group. And on top of that, it's rigid. Okay, so the groups that appear here, so for example, this is the case, for example, when you have 2 generators and 1 relation. Okay. So this gives you many, so I didn't say it's finite, I didn't say it's not empty, but actually it's not empty. We can even find a lower bound on the size of that set. It's at least L over log L, and it's at most L to some power. So we have here a collection, in fact it's a single Galois orbit, a collection of algebraic points, because since it's finite, it's a single Galois orbit, the points will be algebraic, so the algebraic entries. And they generate a certain Zariski-dense subgroup of G, for which we know that it's rigid. But we don't know, well, so we know many examples of rigid groups. They come from S-arithmetic lattices. So the obvious question is, are these groups actually S-arithmetic in disguise? And I have no clue about this, so that's the question. Are the groups, the Zariski-dense groups arising when r equals k minus 1, so that's when defect is 1, S-arithmetic. So we know they have algebraic entries, but we don't know if they are S-arithmetic. They could be lattices. With high probability, yeah. Yeah.
You have many W's, so give you this finite collection, so it may be the same collection for all W's.
No, so for each W, you have a collection.
Yeah, but
if you change the W's,
so it could be the same collection that you get over and over again.
no, because the size grows with L. So the size we have some control on the size of the Galois orbit. So if L is very large, then it's going to be different. It's going to be another group. Yeah, part of the problem why this is not so clear is because the groups are defined by generators, and who knows where there are finite index somewhere. Okay, so now I will discuss a couple of things about the proofs. So I mentioned.
You just make r equal 2 and k equal 1. This is it's unrelated. Why should they be as argument? What's the connection?
The image, not the group itself. But, yeah. Because these are local. Yeah. So yeah. So the group arising. I mean the image under the representation. Because these are rigid, and there are not so many rigid groups that people come up with, except from S-arithmetic groups.
You just gave an example of two related one related to two generator groups. That is rigid.
That's right, but I don't know what's the. Is it S-arithmetic? It could be. Yeah. Yeah. So these groups are defined by generators and relations, but. So you know the generators, you can identify them, but you don't know what's the group that generates. Okay, so some idea about the proofs. So as I mentioned, as I hinted, this idea of Liebeck and Shalev, where what we're going to do is we're going to reduce mod P and get a hold on the character variety by counting how many points it has mod P. Okay? So the idea is in 2 words. I mean, it's basically Chebotaev. What does Chebotaev tells you? If you have a variety defined over Q, then you can read off its dimension by counting how many points it has in mod P. You count x of P divided by log P, and the lim sup of this is the dimension. I take lim sup, not lim, because sometimes there are no points in mod P, or there are fewer points. Depends on the prime. And on the other hand, if you want to count the number of connected components, you need to average over primes. So if you average over primes the number of points of x of P divided by P to the power the dimension of x, what you get as t tends to infinity is exactly the number of Q irreducible components.
Irreducible components
of maximum dimension. Thank you. Okay. So, so this is the general fact for every variety X, but as you can see here, it involves a limit when p tends to infinity. The problem that we face here is that this is t. Is that our varieties they became wider and wider as L, as the length of the relators go to infinity. So it's all going to be a fight between L and P. So we're going to need to find a P for which this holds, but not too large for it to be meaningful for L. Okay. So yeah, and so for this we need some kind of effective Chebotaev. So we need effective versions of Chebotaev. Let me maybe finish here. Yeah, so we need effective versions. And this is where GRH comes in to control the error term in here. Okay. But maybe I'll just end by putting like the main idea in just one line. Main idea is to use Fubini, where you double count the size, this size, the number of FP points in the character variety. You double count it by averaging over the primes, and this is where Chebotaev is needed. And you double count it by averaging over the words. And for this, what you need is mixing. And what you need is exactly theorem 1 of my talk this morning. Okay. So, because the point is, if you write down the expectation of XW of P, this is exactly the expectation of the sum over all pairs AB. Suppose I have k equals 2, r equals 1, of the indicative function of W of AB equals 1 in the group mod P. Okay, so it's just a sum over pairs of the probability that W of AB equals 1. So it pairs up to conjugation. And here you need to say, well, you need to understand this probability. That's exactly the mixing. But the mixing for what generating set? For the generating set AB. And you sum over all generating sets. So you need control. You need the expanding property for all generating sets. And so so you need to take L to be roughly log P, so that this becomes equidistributed, so it becomes 1 over G. So it's going to become the sum over 1 over G of P over all conjugacy classes of pairs, and so therefore it's going to be close to 1. So it's going to be G of P, the number of conjugacy class of pairs, divided by G of P. So it's close to 1. The fact that it's close to 1 will tell you in this case that this is a finite set. Yeah, so it will tell you that there is a unique Galois orbit also. So here, this sketch is for 2 generators, 1 relator. But the same thing works in arbitrary, arbitrary K, arbitrary R. So, for expansion, I talk about 2 generators, but when you have more generators, it's also fine, because, yeah, I mean, for generation, for expanding, for expansion, if you can prove expansion, uniform expansion on 2 generators, you can prove uniform expansion of K generators.
2 elements don't generate all.
2 elements will generate G of P. if you have k elements, you can find 2 elements that generate within a bounded ball, KD ball. So expansion for pairs implies expansion in general. So that's not an issue. So the fact that it's 1 here tells you that the number of connected components is 1, the dimension is 0. So in this case, it tells you this case. Yeah, give you this in that case. Okay, so I'll stop here. Thank you.
Are there any applications of this result?
A good point. So for me, this was the application of the uniform mixing of the modding, but it's also related to. So I mean, in some sense, it's an offshoot of work I did with Peter Varju before, where we were interested in random polynomials in one variable. And we showed that random polynomials of very long length, very long degree, are irreducible over Q. So here, this is kind of a non-commutative version of this. Are there applications of this? It could vary. So it could be that there will be. My hope is that maybe understanding the geometry of these world varieties will help understanding problems related to spectral gaps also, and in general. So and understanding word maps as well. So with we have ongoing work with Itay Glazer, who's in Haifa, couldn't come today, but where we push this a little bit further, where we study singularities and smoothness of word maps. So yeah, so there are applications, but